All right, I think I'm live at this point. So to begin with, are there any particular questions from you to me about where we're at in the course at this point? Anybody having trouble finishing the first assignment? I hope not. It's mainly just about getting everything up and running, making sure you have things moving around. You can get input from the mouse, input from the keyboard, put things in kind of little containers or data structures and make sure you're keeping track of everything that has happened. Just little things like that. So if there are no questions on that, I just wanted to begin by diving directly into the window to viewport mapping, seeing as we've already kind of looked at that, looked a little bit at playing around with the values that we send into GLU Ortho 2D, which is kind of our window that we're drawing into, and GL Viewport, which is the viewport drawing on the screen. If you've kind of experimented with the values there, you've gotten a little bit of a feel for what the window to viewport mapping does. But we're just going to look at how it's actually calculated. So I'm going to start on this side of the board and do something that I'll probably do several times over throughout the duration of this course, which is draw up the overview image of the Opengl pipeline. So our Opengl pipeline is here. We send vertices in. In our case now, we have the GL begin and GL end. This will change to kind of vertex lists and stuff when we start using shaders. But for now, we're telling Opengl we're going to begin sending things actually through the loop, and we're done with that. And in GL begin, we tell it if it's going to be triangles or lines or triangles, strip, or however it's going to process these individual vertices. And then we call GL vertex. Here in our case, we used GL vertex 2f, which means we just send two values in, and they're floating point values. The third value is z, and that's just always 0 when we do that because we're working in 2D. Later on, we'll use GL vertex, or we could use GL vertex 3f or even 4f. But we're going to do that differently when we start using the vertex lists. So vertex, 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 in. Here we have our vertex shader with these different matrices here and some lighting calculations happening as well and stuff like that. So we have the model matrix, the view matrix, projection matrix, into clipping, and finally here rasterization, where we also have the fragment shader. This box here is what we're going to be looking at now. So we have two-dimensional, three-dimensional continuous coordinates going throughout here. In the end here, even though we're working with 3D here, after the clipping and the projection, here we're working with two-dimensional continuous coordinates. After clipping, we go into window to viewport mapping, and we can talk about whether these are continuous coordinates still until they go through the rasterization, or if they're now discrete coordinates for a pixel. For now, we're going to view them as discrete coordinates. We're going to say this is where it happens, where we actually go from our continuous arbitrary space into the actual pixel space of the screen. So here we have two-dimensional coordinates, but they're kind of in pixel space. Whether they're discrete or not, that happens around here. So we're going from our arbitrary world into actual pixel space. So here we have window to viewport mapping, which simply means we're going from our world window and we're going into the actual viewport on the screen. And we're going to take our pixels from one representation and into the next. Like so. So feel free to raise your hand, ask questions at any point. At this point, I'm going to draw on one side our window, and on the other side our viewport. It may be misleading that I drew them almost exactly the same size, but they're not. You skipped them in that. I have a different camera here for this technology. Hi there. Doing computer graphics. It's kind of low. I'm wondering afterwards what this view will look like. Me kind of standing super tall with this huge whiteboard here. It'll be impressive. So I want to see what this looks like. Again, people who are just watching this online, let me know if the sound quality is not good, if the image quality is not good. And I'll try to fix that as we roll. So I have the window, I have the viewport, and these are completely different kind of areas. One is kind of what we're looking at our arbitrary world through. The other one is just actual pixels on the screen. And I'm going to throw in a few positions on this kind of. I'm going to say here we have the window left, or W.L, and I have the window right. I have the window bottom, and I have the window top. I could also say I then have the window width and the window height, but I can easily calculate this from the other one. So whether we start with width and height, or we start with left and or right and top, doesn't really matter. We can calculate around that. So for now, let's look at all of these with just the left and right side, the bottom and the top, and then the same for the viewport. We have then viewport, which is V, left, viewport, right. We have our viewport bottom, and we have our viewport top. So now the question is, what data exactly do we have here, and what data do we want to get out of this? So what data is it that I'm going to be working with here? What am I trying to move between these windows? And how exactly does that work? Not really taking data from one place and putting it into another place. I'm just calculating different proportions for different values. So the values I have, if we can imagine, here that we started with 3 dimensions, and we have just some arbitrary space. I have some eye that I'm looking at this from. I have this box here. I'm just looking at it. After the projection, I've kind of taken this onto this screen here. So now I have this kind of 2-dimensional image of this box. So we're kind of looking at just one part of this, like one triangle out of this. If something was outside, I've clipped it in the clipping. At this point here, before window to viewport, I have my window. I know after the projection what the left and right and top and bottom sides of this window are. And I also know the coordinates, kind of x, y, coordinates of the vertex that I'm working with at this point in this window, or actually in my entire world. So this world here might actually be such that, 0, 0 is somewhere far away from this, or 0, 0 might be within this, or 0, 0 might be somewhere high above this, just somewhere else. So my window left and window right and window bottom and window top and x and y in these coordinates, they're all represented in this same coordinate system here. They're represented in my world coordinate system. So if we go back to here, these here are represented in some world coordinate system, and I have some point x, y represented in this same world coordinate system. And again, the center of this might be here, 0, 0. Center of this might be just somewhere here, 0, 0, or somewhere far away where it wouldn't even fit on this whiteboard. But the only thing I know is all of these values that I have here, the values for the dimensions of the window and the point itself, they are all represented in the same coordinate system. Now, what's my objective with that? Can anyone kind of decide for me what's my objective? If this is the window I'm looking at my world through, this is a point that I have, yes?
Are you trying to change from from world space to pixel space?
Yes, I'm trying to change from world space to pixel space. That's what I'm trying to do. So if we can get a bit more detailed than that. I'm changing from world space to pixel space. So I want some point, but what do I want its coordinates to be? Like, what do I want? What facts do I want to be true about the pixel or the vertex that I end up with after this transformation?
Want to be relative to the view you have?
Okay, so I want it to be relative to the viewport, or positioned relatively to the viewport in exactly the same space as this is positioned relative to the window. That's basically my objective. I want to take this point and make another point, or make another vertex, let's say. I'm not really moving a point. I'm kind of finding new coordinates for the same point. I'm just representing it in a different coordinate system, or a different coordinate frame. So I want to find the coordinates, and I'm going to call them Sx, Sy. The coordinates that are proportionally positioned exactly the same within the viewport as my original point is within the window. So, is there anyone who can think of kind of a place to start? You can look at this and see the big picture, but we kind of want to go into details, like what's the first thing I want to do? Things like, yeah, sorry.
Different size?
Well, what size? It's kind of more like, like distances between objects here. Yeah, the difference in the size of the windows. Okay, I'm interested in that. I'm interested in the difference between the size of the windows.
Do you lower the size of the window part for right and left and top and bottom, and then do the same for the coordinates so they match when those are 0?
Okay, so this idea is, do I take this window and kind of squeeze it together until it's the same size as the viewport, and see what calculations do I need for this window to become this?
And then use it on XY.
Yeah, and then apply those same calculations to XY.
Yeah.
That's more or less what we're going to do. Do we need both X and Y at the same time? Do they have an effect on the calculations, or can I do it independently? Can I just do X first and then just do Y, and it won't have? How do you feel about that?
I think so.
Okay, so in this case, that's something I can do. And in a lot of cases in computer graphics, we can simplify our calculations by saying, okay, I'm just going to think about this from one dimension, and I'm just going to do it in that dimension. When we, however, get into something like rotations and camera position and orientation, we can't do this anymore. Then all of the dimensions are affecting each other. But here, everything is parallel or perpendicular to the axes of the base coordinate frame here. This is just horizontal, and this is just vertical. Which means that I can just say, okay, I'm going to look at this only with X. So I'm going to simplify this a little bit and say I have X here, and I have some distance here, and I have some distance here. I have Sx here, and I have some distance here, and I have some distance here. So again, if I'm just going to do this for X now, and I want to do something like Sx equals something, 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 X, something, something. Right. I just want to make a nice formula here where I can put X into something, and it'll simply and it'll yield Sx. Just one nice function. Sx as a function of x. Before we write that function, we can do this in smaller steps. In the end, we're going to make a little function, and our computer can just use that directly. For now, we're going to kind of step by step figure out what that function is. So, what do I want to be true about all of these proportions that I have here, about all of these distances?
The longer distance divided by the other is the longer distance of the other one divided by it. The ratios are equal.
Yeah. So the ratio between this distance and this distance should be the same as the ratio between this distance and this distance. This is something I want to have true. Or I could say the ratio between this entire distance and this distance should be the same as this entire distance and this distance. You know, just either pick two distances that are the same in this image, take a ratio and do the same here, and we want that to be equal. Or I can also say I want this entire distance divided by this entire distance to be the same as this distance divided by this, right? So I take one of these and I want these to be true. So let's start there. I'm wondering if I could utilize the space a little bit better here. Let's draw the viewport just a little bit smaller. Here we have viewport left, viewport right. We have Sx. Somewhere up here we have Sx, Sy. We have viewport bottom, viewport top. All right, so some proportion here I would simply want to be the same. So let's say I take this divided by this and say I want it to be equal to something. So that would be Sx minus viewport left divided by x minus window left. So what ratio can I take and say I want this to be equal to that?
Window right minus window left divided by window WR minus.
Okay, so viewport, yeah, viewport right minus viewport left divided by window right minus window left. All right, so is this something that we feel we could, so is this enough? If I just say, okay, for this to be the correct point, I need this to hold true. Can I now simply make my little formula that says Sx is some function of x? It's not s dot x, it's just Sx. So can I math this somehow and make it true? I can at least say then Sx minus viewport left equals x minus window left times viewport right minus viewport left. We can see that this here is simply a ratio between the widths, right? It's the width of the viewport divided by the width of the window. It's simply a ratio between the widths. So I'd kind of like to isolate this, right? It would be nice to go up here and say, all right, I'm gonna make a variable. I'm gonna call it A, and I'm gonna say A is simply viewport left, right minus viewport left divided by window right minus window left. So A here is the ratio between the widths, which means it's kind of a scaling factor. It's a scaling factor from the size of this window to the size of this viewport. So my scaling factor A is here, And thus, I'm going to erase this and just put A in here so our calculations are nicer. So how can I finish this? I just want Sx to be a function of x. And it'd be really nice also to isolate x somehow in that, so we can simplify our formula even more. Sx equals viewport left, I guess plus, I'm going to calculate out of this x times a minus window left times a. Then I'm going to turn this around a little bit and say Sx equals a times x, right? So I just scale the x with the x scaling factor plus the left side of the viewport minus the scaled left side of the window. Does this make sense to us? And can we read something out of this other than just mathematical jumble? So what's happening is I take this x and I say I'm going to scale it at least to get the sizes in this window into the kind of relative sizes here. So every unit that I'm working with will now kind of be represented in this viewport rather than the other one. The next thing I do is I take this left side here and I add that to it. So I'm kind of adding the left side of this new window, but I'm subtracting the left side of the old window. So again, well, to translate really, I've already scaled. Well, I need to scale.
I was saying subtracting the left side window to scale.
Yes, exactly. So I'm taking this left side of the window. I'm also scaling that into that image, like I do with the x-coordinate. Once I've scaled that, I can say, okay, this is in a different location than this. So I'm taking the corner, and I'm saying I'm going to subtract this corner from it, taking it down to 0. Then I'm going to add this corner to it, taking it into this corner. So this is basically what you talked about, which is I'm setting up a calculation that will take this window here and line it up with this window. So I've taken the size or the width of this window and I multiplied it with a scaling factor that will make this width exactly equal to this width. Then after I've taken that, maybe I've somehow put my window, kind of here. So this is the scaled window. All right? Then I have to subtract its point here, but its left side has been scaled as well. So I subtract that to wherever 0 is. And then I've got my window somewhere here. And then I add this and put it here. So I'm not only scaling it to size, I'm also lining it up with this window. So what this calculation does is it takes each corner of this window and lines it up with the corners in this window. If I then take that same calculation and apply it to this point, then this point will proportionally be inside this window where the other one is. So if I have a full image with kind of 3 points here, it'll end up being kind of proportionally the same image. I'm going to add one more thing here. Then I'm going to say, I'm going to make another constant here called c. It's not a constant, but it's a variable with a value that we can calculate for a certain window and viewport and then use from then on. This also sounds like a good idea in computer graphics to say, I'm probably going to be drawing a lot of vertices, a lot of triangles using the same viewport and the same window, right? So rather than doing these full calculations of A and C every single time for every vertex, instead I say once I've set the window and I've set the viewport, I can calculate A and C. And then I've taken a lot of these calculations and said I can do those once for 1,000,000 vertices. The only thing I need to do to each vertex is then just the scaling part and the translating part that applies to x individually. So I'm going to take this constant part here and say v viewport left minus the scaled window left, or let's have it in the other direction, in the other order. viewport left minus A times window left. So the scaled window left is subtracted, viewport left is added to line the corners up. And then I can say, all right, this then means I can take this out and say this is A times x plus c, which is just the simplest linear formula or linear function that we can have. Yes?
Because when you were explaining the translation,
Yes?
you went down and then to the right. But you can only go left and right when you have to do an essay.
Yeah. Okay, this is true. My explanation kind of imagined that we had both x and y in this. But this is true. We're kind of just looking on, then I shouldn't even have drawn the window. I should have just worked on this one-dimensional timeline here. So my explanation earlier kind of assumed that we were working with both x and y. But this is true, I can't go kind of down to the left. But anyway, after I kind of do the original scale, I kind of found some place here, but then I have to subtract the old corner or the old left side and add the new left side to completely line things up. So for those of you who just like to say, all right, I have these proportions, I know they're supposed to be true, then I just do the math, and this is the math, that's good. So we know this is true because the math is correct. For those of you who just like to look at these things and kind of understand graphically how it works, that's the explanation. We're kind of scaling it first, and we take the scaled left side or the scaled left bottom corner, subtract that to kind of lose the point of origin of this window, and then we add the point of origin of the viewport and thus line it up. Now, we could go through all of this for y as well. Or we could just go ahead and say, can I somehow take just my final result, which is Sx equals A times x plus c, and these, not quite constants, but pre-calculated values, and can I just write up here what they will be for y? Like if I'm going to do the same thing, say here, Sx equals A times x plus c. I just want to make another one for xy. Sy equals
something other than A, where you change right and left to bottom and top.
okay, cool. What are you going to guess I'm going to call the next constant?
A prime.
Sorry?
A prime.
No?
I would like A prime.
A prime, all right. The reason I used A and C here, all right, the reason I do this is because the book that I originally learned this from used these letters, and so I've used them since. Of course, we could use anything. I'm going to use B. So the scaling factors are A and B. The translating factors are C and
C prime.
yes, question.
Isn't it also just tied to the order in which you would write these into a matrix?
Yes, it is. Let's look at that in just a jiffy. Since we haven't done matrices before we did this, I can write up the matrix, but we'll understand that better later for those of you who haven't. All right, so what will B equal here?
VT minus VP.
All right, so viewport top minus viewport bottom, which is basically the height of the viewport, divided by world top minus world bottom. All right, so we've simply got a ratio between the heights, same as we had a ratio between the widths. Cool. D, like somebody said after you said C prime. D equals then what? Viewport bottom, yes, minus B times window or world, whichever you like the W to stand for. And Sy then equals, it's going to be a nice linear function as well. What does that look like? B times Y plus D. All right, so we have Sx equals Ax plus C, Sy equals By plus D. For those of you, which I imagine are a lot actually, that have already taken linear algebra, and when we go into matrix multiplication. It'll just be a recap for you, but I'm still gonna take that somewhat from scratch. We can imagine that our point Sx, Sy, I'm just gonna stick a 1 here and explain it in a week or two, equals the matrix A and B for scaling factors, C and D for translating factors, times X, Y. All right, so if we do this multiplication, this matrix multiplication for X and Y, we always get the point Sx, Sy out. So in our graphics hardware, because a lot of the things that happen in the vertex shader are matrix multiplications, and these are done for every single vertex in the entire scene. Our graphics hardware is optimized for doing matrix multiplications, for doing linear algebra, for doing this kind of thing. So we have this amazing hardware that's right next to where our images are being drawn, and it's perfectly optimized for matrix multiplications. The obvious choice for window to viewport mapping would be to set it up in such a way that it can take scaling factors and translating factors, put them into a matrix as well, and do my window to viewport mapping in a matrix multiplication as well. So that's what happens kind of in reality inside our graphics hardware in the end. At this point, we have, after clipping and after everything, we have this set of vertices. As soon as we set up a new window in viewport, A, B, C, and D are calculated. They're put into a matrix that resides in this window to viewport mapping algorithm. And then we never have to change those values or change that matrix. We're just throwing the points that come out of the clipping into that matrix multiplication, and it happens, it's the fastest calculation that we can do kind of inside our graphics hardware. If we, however, change the window or the viewport at some point, then those need to be recalculated. So these here will be recalculated just when we actually change kind of our point of view, viewport or window, but they don't need to be changed between that. Did we start? Okay, cool. Are there questions regarding this? No? Because it's all clear? Or because you don't know exactly what the question should be? All right, so this isn't super complicated, and this is something that's just nice to start with, to kind of get to the understanding of what's happening inside the graphics pipeline to begin with. These boxes that I draw in the pipeline, they're just kind of encapsulations of these different algorithms or different calculations, and this is just one of them.
Will we be doing this ourselves when we make bigger projects? Or?
Okay, so the question is, will we be doing this ourselves? Not in OpenGL, not in your programs, no. This is one of the things that just happen in the pipeline does it for you. So when you're doing your programming assignments, no. When we are just kind of, well, this is kind of part of how this course is split into two, in effect. That we have the programming assignments where we use OpenGL and we try to utilize the power of OpenGL as much as we can. And so, calculations such as this are just hidden from us and they just happen. We set up the viewport, we set up the window, but the calculation happens. The kind of other half of the course is just doing kind of smaller assignments, written assignments, hand-in assignments, and the exam itself, where we actually perform these algorithms by hand, and we do these calculations just as math. So it's split between the two, of kind of hands-on applied programming course with OpenGL and a mathematics course of linear algebra as it kind of as linear algebra has to do with computer graphics.
Could we use this to maybe decide on what size of viewport we want to use?
That's a good question, actually. Can we use this to decide on our viewport? Yes. Specifically, you can use it to kind of decide on the proportion of your viewport. That is, you've already set up the window, and then you have some screen that you're going to put it into. If your window kind of doesn't fit into the same proportions of the viewport, you're going to get a skewed image. So there's a lot of kind of knowing this that you can use in order to make sure that the window you're drawing into, for instance, is the same proportion as the viewport. If it isn't, then either you have to start the viewport in a different place. So trying to get these proportions right, yes. Deciding, yes, on the size of the viewport and so on and so forth. This is something that you can use this for, most definitely. And that's maybe a nice point to wonder about another question. So, window and viewport, what happens if they're not proportionate? What happens, we've only been looking at proportions between width and some other width. You know, one width and another width, one height and another height. What happens if we look at the proportion between width and height? Will these calculations fail if the proportion between width and height in the viewport and the window don't match? Not really. I imagine if our viewport looked something like this, and we draw this image in, our image is just going to be something like that. It's just going to be squished. We're going to get the same proportion horizontally and the same proportion vertically. Is there something that I can look at when the calculations are in the values that are pre-calculated and just see right away, okay, this is out of proportion, I need to fix this. If I don't want my image to be skewed, I can fix the proportions. Is there something here that I can just look at right away and say, this image is going to be skewed? Yeah?
A and C.
A and C? Are you sure?
A and B.
A and B?
Oh, A and B.
Yeah. Okay, so A and B are both the scaling factors. So if the image is proportionally correct, or if we have the same proportions, what do we know about A and B? Or what will the values of A and B be?
They're equal.
Yeah. So if A equals B, then we know the proportion is correct. If this matters to us, we can do something with that. We can, in our own program, calculate these. Obviously, these are calculated kind of in our graphics hardware. It's all hidden from us. But we can still, if we know how this works, we can go ahead and just calculate them ourselves. We know a lot of these values, and we can see kind of how we want this set up. And again, something like saying, all right, I have this window, and I need to draw that. Then I have, if we draw the viewport a little bit differently, I simply say, rather than this being the viewport, this is just my program. And it has, you know, a header here and some stuff up here. It has a border. And I know what area I have here. I know kind of my canvas. And in some cases, I might want to say, all right, I want this proportion to be correct. So if this is a little bit more squished, I actually want to have my viewport start a little bit further from here and end a little bit further from here so that it kind of fits in the center of the screen but isn't skewed. If this image, however, is flatter, I want to do it the other way around. I want to put my viewport here so that this image, even though the window is like this, for instance, if it's a window that the user can just come here and kind of put their mouse here and start dragging it around and resizing it, but we don't want that to skew our game that we're programming for them, then we can do something like this. If I just pull it down and make it really tall, I'll just make sure my image just starts a little bit from the top, ends a little bit before the bottom, and it keeps its proportion. If they, on the other hand, pull it somewhere up to here, so that it gets really long, I'll do it the other way around. I think this would be a nice exercise. I'll stick it into your programming exercises for next Monday. How about that? If someone can do it beforehand, you know, you can show us at the beginning of the class. Other questions regarding this? So yeah, after you've calculated this, like when you're doing it by hand, just to kind of sanity check what's happening, you can say, okay, if A and B equal each other, these are proportionally correct. If not, they're not. other than that, like I said before, the x dimension and the y dimension can be completely separate in these calculations. So they have nothing to do with each other. So if they're not proportionate, x just happens in its own x space, y happens in its own y space, and the final image that we get may be squished or something, but it won't ruin the calculations. Calculations will just happen as they are. I think now is a nice time for a short break, and afterwards we'll just start looking at vectors and stuff a little bit. Jó.
Klipping ég veit ekki.
Já, bara hvað það gerir.
Þetta nýtt koncept fyrir mér, sko, ég kom aðeins seint í áfangan, sko.
Það er bara aftur því að undirklipping sko, hugmyndin er svo að ég er bara með einhvern glugga hérna sem ég er að horfa inn í, að ég er búinn að setja inn glugga sem ég horfa inn í, eða í þrývíð, ég er búinn að setja myndavél sem ég horfa í gegn. En ég er ekkert að fara að tékka fyrir hvernig einasta hluti er nákvæmlega inni eða nákvæmlega úti eða hvernig það er. Þannig að það getur vel verið að ég teikna einhvern hlut sem fellur ekki eins og inn á skjáinn. Klipping kemur til með, einfaldlega að henda þessum hlut og segja að það þarf ekki að gera neitt meira með hann og spara okkur restina af þessu. Ég geti líka teikna margirning að hluta til inni. Og aftur, af því að hardware okkar, graphics hardware er svo miklu betur bestað til þess að díla við allir þessar hluti, að þá vil ég að það sjá svona hluti. Kannski get ég gert hraðvirkari leið sjálfur til þess að komast að eitthvað er alveg fyrir utan skjáinn. Þegar svona eitthvað kemur upp, þá sér klipping það. Basically finnur punktinn, ef einn punktur er fyrir utan og annar inni, finnur það þennan skurðpunkt og í rauninni hendir þessum punkti og býr til nýjan hérna. Saman með þér. Og segir, ok, þessi þarna var fyrir utan, nú er ég búinn að búa til margirning sem að öllum hlutföllum er eins og hinn, maður bara vantar á þann hluti sem er fyrir utan. Þú getur haldið áfram hér inni. Því rasterization, þegar við erum komin í raunverulegt pixel space, þetta var í rauninni window, þegar við erum komin með þetta yfir í viewport, þá er þetta hérna bara annarkvæmt fyrir utan skjáinn, eða hluti af skjánum sem okkar gluggi má ekkert eiga við. Það er klipping.
Það er bara að taka áferða sem við munum ekki sjá.
Já, og við erum ekkert búin að læra hvernig klipping virkar, við gerum það fljótlega. En það er hugmyndin með klipping, það er bara að tekur þetta út. Við þurfum ekki að eyða tíma okkar í restina á hluti sem er ekki þarna.
En eitt hérna með window, ég er bara að reyna að pæla, sko, window er hérna, ef við notum einhver svona indiföll eins og til dæmis til að finna út hver edges eru fyrir hérna, í verkefninu náttúrulega að passa að kassin geti ekki farið út fyrir.
Já.
Þá nota ég til dæmis eitthvað eins og game height og game width.
Já, þá ertu að horfa á viewportið.
Er það með viewportið?
Já.
En hvað er það window?
Window er, sko málið er að ef þú setur upp forritið þitt, eins og flestir hafa gert í þessu fyrsta forriti, svo þú segir bara, heyrðu, ég ætla bara að skilgreina window sem er 800 á breidd, 600 á hæð, svo getur skilgreina viewport sem er 800 á breidd og 600 á hæð. Þá sérðu það að A þarna er að fara að verða 1, B er að fara að verða 1. Og ef þú ert með 0,0 punktið hérna niður í báðum tilfellum, þá eru bara C og D að fara að verða 0 bæði. Þannig hérna ertu bara búin að matcha þetta upp og ef þú gerir það, þá getur alveg farið hérna og skoðað einhverju hluti úr windowinu. Pygame gefur þér aðgang að skjápixlunum, það er viewportið. Window hins vegar, þú skilgreinir það bara sjálfur. Þú getur bara sagt, heyrðu, ég ætla ekki að hafa windowinu svona. Ég ætla að hafa window sem byrjar í -1 og er 2 á breidd og 2 á hæð. Þannig að miðjan á hnetakerfinu mínu er hér. Og þá náttúrulega sérðu að þú segir, ok, þú teiknar í þetta. Þannig að það þýðir að hnitin á þessum hérna sem ég ætla að teikna, þau eru hérna hálfur og upp í 1. Þessi nýtt matcha ekki við þetta, en ef þú ferð þá að segja, heyrðu, ég ætla að ganga mér búin að reykast í skjáin með að tekka hvort það er komin í þetta, þá er þú að bera eitthvað saman sem er komið 2 við einhverju tölu sem er 800. Þetta er bara alltaf nær.
En það er svona akkurat...
Þannig að window, já þess vegna þurfum við að skeila það niður. Þannig að sko, leið og maður er hættur að matcha windowinu og viewportinu nákvæmlega, getur maður að lítið nota þessar upplýsingar sem þú færð frá Pygame breidd og hæð á glugganum og eitthvað svona, til þess að affekta leikinn þinn.
Okay.
Þá hugsaðu bara, leikur minn gerist í einhverju game space og ég bara hugsa það alveg sjálfur. Ég langar að hafa 0-0 neðst, ég langar að hafa þetta 10. Mér finnst einhvern veginn þægilegt að hugsa að ég er með einhverja kubba og þeir eru 1 á breidd og þeir passa í 10 og hérna langar maður að hafa þetta 6 á hæð. Þú bara setur upp þinn window, í þrívídd þá er henni fjarlægisnærið ennþá meiri. Þá setur þú bara staðsetning á myndavél og hvert hún horfir og hversu breið linsan er. Þannig að windowið verður dálítið til úr útreikningum. Þú stýrir því ekki eins og nákvæmlega sjálf. Þegar í tvívídd þá stýrir þú windowinu bara því að þér finnst það að hafa leikinn. Og svo er það window to viewport mapping sem sér bara að taka þetta, smyrja því yfir á pixelsvæði hversu stórt sem það er. Snilldin þá er að þú getur stækkað viewportið þetta því að skjárinn er stækkað, því að kemst að full HD skjá. Leikurinn er alveg eins. Ef þú ert alltaf fastur í að matcha leiknum þínum við viewportið, þá leið að þú allt í henni kemst á hærri upplausn á skjánum og þá er leikurinn líka bara að gerast miklu minni hluti á skjánum. Þannig að þetta er bara decoupling, þú vilt bara hugsa í þínu gamespacei, þínum stærðum og leiða window to viewport mapping að setja í pixlanum.
Ok, þannig að það er líka þegar við erum með resizing og window og drögum, þá er bara konstantið að gera þessu fyrir.
Já, eða sko, þetta er að gera þess að þarna útreikningar, sem sagt, formúlum sjálfa, S6 er þetta, X plus Y, það er að gera það í einhverjum einasta rammakur fyrir einhvern einasta hlut hvort sem er.
Já, ok.
Leið að þú ferð að resize eitthvað, það sem gerist þá er að þetta bara endurreikna A, B, C og D. Það eru ódýrir útreikningar til að gera einu sinni per ramma. Það eru mjög dýrir útreikningar til að gera einu sinni per vertex. Þannig að ef þú verður eitthvað að draga til, já, þá endurreiknast A, B, C og D. Ef að þú ert bara að hugsa í þínu eigin gamespacei, að þá dregur þið hérna til og leikurinn bara tegist yfir það. Það er kannski þýtt, en kannski þýttir það ekki. Ef að þú ert eins og að fastur í að hugsa í 600-800, það er að draga þið hérna til og ert að nota þarna, eins og segir, pygame.getWidth og getRight og eitthvað svona. Þá getur alltaf leikurinn þinn verið að teiknast hér, en samt einhvern veginn lent út fyrir.
Það er svona bad practice að nota eitthvað svona innbyggt.
Það fer alltaf eftir hvað þú ert að gera. Ef þú ert að gera leik þar sem þið langar bara að hugsa hann í pixlum, þá er það fínt. En þá þarftu ekki í rauninni hvert skipti sem viewportið breytist, þá ertu að tjekka á viewportinu og kalla aftur á Windows-skilgreininguna. Í okkar tilfelli núna er glöð, ortho, 2D og það er að kalla aftur á glöð ortho 2D til þess að uppfæra það ef þú vilt vera alltaf á sama pixla.
Er það hann sem þetta glöð ortho 2D pakk gerir?
Það er skilgrein á Windows. Þannig að ef þú vilt leika þig með þetta, bara þá í glöð ortho 2D og breytir gildanum þar til að breyta á window, farið í GR Viewport og breytir gildanum þar til að breyta viewportinu.
Hvað ef að gildin eru minni í glöð ortho 2D heldur en í viewportinu?
Skiptir engu máli. Þú getur sagt að þegar gamespacei mitt er þannig að ég er að teikna plánetur hérna. Þessi hérna pláneta er 1.000.000 kílómetra frá þessari hérna plánetu. Þannig að gamespacei mitt er fyrst með mínus 10 milljónir hér og það er með mínus 1.467.000. Þetta er alltaf. Þetta er með þess að flippa, ég seti mínus hér fyrir nei, ok. Þú skilur, þetta er bara gamespacei þig og þá er netið bara þannig. Ok, þessi hérna pláneta er á 9.100.000, það er bara verkefni þínu svona. Það er alltaf því að window to viewport mapping tekur stærri hluti, skala niður í viewport, þannig að það tekur litla hluti, sem er einhver microscopic skala. Windowið þitt er arbitrary space, það er engar mælieiningar. Það eru bara hlutföll. Þú þarf bara að hugsa þær mælieiningar sem þér líður vel. Ef þú hugsað í metrum og teikna plánetur, þá ertu með risastórar tölur. Ef þú hugsað í metrum og teikna sameindir, þá ertu með pínu litlar tölur. Bæði er allt í lagi vegna þess að window to viewport mapping tekur yfir í discrete absolute gildi sem eru pixlarnir. En þangað til þá vinnur þú bara í þínu pixel spaces. Nei, ekki pixel spaces fyrir ekki, þínu bara world spacei.
En maður hugsa samt alltaf allt í viewport spacei. Því að þú veist að miðast allt við pixlana.
Já, núna, þegar þú ert
maður gerir svona 2D basic.
Já, en ef þú býr bara til Windows og segir glöð 2D hjá mér, sem er eitthvað mínus 10 bóða, þú bara nota þau gildi til þess að skoppa. Sagt að ég veit hver minn ímyndaði veggur er í þetta, skoppar af því.
Já, en þá þarf að mynda hann að matcha viewport.
Það þarf ekki það. Ekki ef þú notar tölurnar sem þú ert að tala. Þú segir að windowið mitt er bara alltaf frá mínus 10 10. Þá segir þú bara, ef þessi kassi hérna er komin upp í 10, þá ætla ég að snúa hann við svona skokk tilbaka. Þessi kassi er komin niður fyrir -10, snúa hann við svo hann fær tilbaka. Svo teiknar hann inn í þennan glugga og staðsetningarnar á honum eru...
Já, en ef þú skeilar sér niður, þá er hann ennþá að miða við 10 windowið, en viewportið er kannski þá ekki...
Nei, svo bara tekur Opengl window to viewport mapping, tekur bara það sem þú teiknar hér inn í þennan glugga, bara setur það í pixel spaceið þitt. En í þessum fyrstu verkefnum þá skilji það mjög vel að fólki þykir þægilegt að vera bara að matcha viewport og window og hugsa bara í pixlum og það er allt í lagi í gegnum þessi fyrstu verkefnum. Svo förum við í þrívít og þá er það bara ekkert hægt lengur. Þú getur ekkert hugsað í pixlum í þrívít, þegar um leið að færi hluta aðeins lengra frá, þá tekur það minna pláss, þú veist.
Akkurat.
Þannig að það er ágætt að átta sig á hugsuninni að windowið, arbitrary spaceið á það sem gerist í vertex setunum og í rauninni hnitin okkar eru skilgreind. Það er algjörlega kúplað frá viewportinu, pixlunum. Þú getur bara leyft þér að hugsa þetta þannig að þetta er algjörlega aðskilið. Þannig að window to viewport mapping bara tekur þetta úr heiminum sem þú hugsar í og bara plantar þessi fyrir pixlunum. En þangað til að þá þarf þetta ekki að hugsa í pixlunum. Það er gott að, þú veist, vinna aðeins með þetta í tvívítinni. En þegar við förum í þrívítina þá er ekkert option lengur að hugsa í pixlum.
Nei, en mér finnst alveg jafn mikilvægt bara að skilja tvívít,
En það er líka allt í lagi að hugsa þetta bara í pixlum. Það er alveg góð hugaræfing út af fyrir sig líka. En þá þarf maður líka að fara að pæla í hvað gerist ef einhver risa eins og bara gluggamann hans. Þá þarftu að fara að stækka windowið með og hugsa allt upp á nýtt. Eða getur þú bara sagt, skiptir ekki máli, en ég kúplaði mig bara frá pixlunum. Ég bara hugsa þetta í mínum heimi, ef ég stækka glugga, þá skjúast leikurinn minn. Sérlega fínt. Eða get ég þá kannski sett viewportið mitt þannig að það skalist ekki, heldur bara taka eins minni hlut af skjánum. Ef ég strekkir að hinga á lengra þá bara læt ég viewportið mitt aðeins hreyfast til með portioninu á windowinu mínu. Og þú gerir það bara í þínu eigin space, þú gerir það bara með tölum, þú bara veist hvert proportionið í þínum ímyndaða glugga er, forsa það yfir á viewportið. Þú fær þjálfun í þessu á mánudaginn. Smá fórhaldum með hjálp og það kemur þetta betur í puttana. Já, algjörlega. All right. Let's just do a little vector recap now. Vectors and points and kind of coordinate systems. Let's just look at coordinate systems and coordinate frames. Vectors, points, just so that we have kind of the same lingo going on here. So, to begin with, we're all familiar with kind of a regular coordinate system. And I'm going to draw that in 2 dimensions here for now. Within this coordinate system, when we have some coordinates, we simply imagine that we count the first coordinate along the x-axis. So if we have a point 3, 2, simply go 1, 2, 3 for the x-coordinates, 1, 2 for the y-coordinates, and we have our point 3, 2 here. When we start working with 3 dimensions, it's hard to draw it in 2 dimensions here, but we add the z-axis here. So we have the x-axis, the y-axis, and I imagine this z-axis to come towards us if we're looking at the regular 2D coordinate system like this. That makes it a so-called left-hand coordinate system. If we make this point kind of away from us into the whiteboard, that would be a right-hand coordinate system. So I'm going to be working in left-hand coordinate systems and mainly going to be working with OpenGL like that, and for now we're just going to trust me with that. Left-hand coordinate system. You can go online and read about why one is called left-hand and the other called right-hand. You can do like a thing with your left hand and then the z-axis will come up towards you, whereas you can do the same thing with your right hand and then kind of x-axis, y-axis, so on and so forth. Left-hand coordinate system, we have the z-axis coming towards us, which means we count the third coordinates like out of here, or if I'm drawing this like this, I just count it like such. So the point 3, 2, 1 is here, kind of hovering in midair. We'll do a lot more 3D later. For now, let's stick to 2 dimensions while we're kind of exploring different ideas here. So this is the point 3, 2 in this particular coordinate system. A point has coordinates that represent, let's call it the point P, that represent a position. So it's an absolute position in space, and it's a specific location. If we instead draw the vector 3, 2, can go in here and say, here's the vector v, which also equals 3, 2. So I draw it again, its length in the x dimension is 3, its length in the y dimension is 2. But I can also go ahead and draw it here and say it's just 1, 2, 3, 1, 2. So here I also have the vector v, and it also equals 3, 2. So the coordinates in a vector represent a length, more or less, or they represent a direction, or we can calculate both a length and direction from it. But we can imagine they represent either a length or a force in each dimension. But a vector doesn't have an absolute position. With vectors, however, we can do fun things, like say I have another vector here, which is called w, and it equals, this would be 1 and 2. So I can take this vector and I can say I can make a sum of these vectors. So I have a certain force here, a certain length, and I can add another force to that. So I can say, if I draw this vector w here as well, I can make a vector that I'm going to call the vector, I'm not going to call it anything, just v plus w, which equals 4, 4, 4. So I have w here as well, it's the same vector, equals 1, 2. This is something that I can't allow myself to do with points. I can't say I have a point which has a certain position, and I'm going to add another point to it. Firstly, when we start working with it, it just doesn't make sense to add positions to one another, whereas it does make sense to add forces to one another. And once we start working with homogeneous coordinates, we'll see even clearer how our calculations will go off if we do this. So a lot of things that are skillgreint, defined, thank you. Words sometimes fall out of my head. I'm going to have to get used to it. Which are defined for vectors are not defined for points. So let's look at a few more definitions here for vectors. If we have the vector A plus the vector B, this equals a single vector that has the coordinates ax plus bx and ay plus by. So these are the coordinates. We can multiply a vector, but we don't really multiply vectors together. We're going to use, however, multiplying it with a scalar. So I'm going to say some scalar here, which is just a number. I'll do a little thing here on top of the vectors for now, but I usually either forget or skip that. So I have a scalar, which is just some real number multiplied with a vector, and that'll give me the vector where the x coordinates are the scalar times the vector's x, and that scalar times the vector's y. So I'm just multiplying this scalar into all of the dimensions of the vector. And we can see if I have this vector v here, I can draw another vector next to it, or let's do it with w here. You can say, all right, this vector here is the vector 2 times w. It has the same direction as w, but it has twice the length. So that's basically what happens when we take a vector and multiply it with a scalar. We get a parallel vector, another vector that's exactly parallel to it, but it has a different length depending on the scalar. Scalar can be negative as well. So we can say this vector here is minus 1 times w, which also equals minus w. So I can then say the vector minus a equals minus ax and minus ay. So mixing these together, I can take a minus vector and multiply it with a scalar, or I can use a negative scalar, so on and so forth. I can more or less, and then I can add that to different vectors. I can do huge linear combinations of vectors. But linear combinations of points don't add up unless in one particular case where all the scalars on the points add up to 1, and it's not one particular case, but it's kind of a set of cases. So I can do a linear combination, which means just multiplying points with scalars and then adding the results up if all the scalars add up to 1. In that case, if all the scalars add up to 1, it's kind of like a weighted average. So I'm basically averaging these points, and in that particular case, it can work. Never mind, I'm going kind of ahead of myself with a lot of this. We'll just look at it clearer later on. What more can we do here? Can anyone think of other operations that we can do on this? There are some specific vector operations, sorry.
Is that division?
Division, yes. We can kind of say that a vector A divided by some scalar, let's just call it t, is the same as saying 1 divided by t times a. So a division is a multiplication as well. You just say, doing it like this, we can just as well divide this scalar with 1 and then multiply with it, so it's going to be a multiplication as well. A subtraction we can take specifically. So a minus b just equals a plus minus b, obviously. But if we want to draw that specifically, when we had an addition of vectors, we took one and then we added the other, and graphically going from the beginning of this one to the end of this one would give us the resulting vector. If we want to look graphically at v minus w, we can draw them both starting at the same point. 3, 2, and 1, 2. So w looks more like this, v looks more like this. So I have v here, I have w here, and then I go from the end of the first vector back to the end of the second vector and say this. No, that's not correct, is it? It's the other way around. So this vector here is v minus W. So graphically it'll look like this. Mathematically we can say that V minus W, where V is 3.2 and W is 1,2, and 3 minus 1 is 2. This equals 2. 2 minus 2 is 0. So our vector V minus W is 2, 0, and that makes sense. This is length 2 in the x dimension, but length 0 in the y dimension, right? So it's just a horizontal vector. So mathematically it gives us 2, 0. Graphically, we make them both begin at the same place, and then we draw a vector between their ends. All right, let's look at a particular vector-specific operation here, which is called the dot product. Everyone learn about the dot product? Cool. So then we won't spend too much time on that. A dot B equals, can somebody tell me what the x coordinates are going to be? Or no, sorry, I'm not going to. Yes.
AX plus times EX.
Uh-huh.
AY times BY.
Plus, sorry, I started doing a AY times BY. Okay, so it's the x coordinates multiplied, then we add that to the y coordinates multiplied, which means that this doesn't yield another vector. It's an operation on two vectors, but it just yields a number. And it actually doesn't matter in how many dimensions we do this. I can continue. I could do some kind of general purpose definition of this, but I'm not going to waste our time on that since we're just interested in 2 dimensions and 3 dimensions. But basically we take each pair of coordinates, or each pair of values from each coordinate, or from each dimension, we multiply those together, and we add the whole thing up. So, if we take the dot product here, specifically, dot product, there are a few things. A dot B equals, for instance, is A dot B symmetrical? Does it matter in which order we do this? If we look at the formula?
No.
No? So A dot B equals B dot A. What about a scalar on A? If I multiply A with a number and then take the dot product with B, can I write this in different ways as well? Like the question is, does it matter where the scalar comes in this whole thing? If you look at this, the scalar will be on all the A things. So the scalar will be on AX, the scalar will be on AY, the scalar will be on AC. Would it have mattered if I did the dot product first and then multiplied it with the scalars? Does that make sense? That if the scalar is on AX, AY, and AZ, and then we add the whole thing up, we're kind of multiplying each factor here with the same scalar. So we could have just as well done the dot product first and then multiplied it with the scalar. This can in fact help us optimize some calculations that we do to understand that we, either way, rather than doing this afterwards after doing a bunch of dot products, we can just do it beforehand to one of the vectors and then use that vector. Or rather than putting the scalar every time into a single vector, we can just take the result afterwards. And this would also be the same as saying A dot S times B. So the scalar, it doesn't matter where we put it in. It scales the entire result in the end. Other things that we can say about the dot product? Probably things that I'm forgetting. But some of these have to do with kind of the orientation of vectors. So I'm going to save this for just a while. Do you remember when the class is exactly over? 14:20, fine. We have 25 minutes now, and we're going to do a little bit of an exercise. I'll just switch over to the other. One thing I'm going to do to save this recording, should have done it at the beginning of the class. Always something you forget. All right. Did I put the both in the same place? Well done. Okay, I'm going to go through this exercise, and as I'm going through it, I'm sure I'll remember kind of more facts about the dot product, and we'll just add them in as we go along. This is a nice exercise to kind of utilize all the stuff that the dot product has to offer. So I am going to look at, am I within screen here? Okay. Can't really go further than this. So I'm going to look at a vector A and a vector B, and I'm going to think about what the angle between them is. And there are formulas to do this, but what we want to do, like earlier with the window to viewport mapping, afterwards we're going to take a formula that we figure out today, and we can just use that directly in our programs and do whatever we want with it. For now, however, we're going to kind of step by step figure that formula out. So is there something that I know about these particular vectors?
Their x coordinates are.
So I'm just drawing them arbitrarily in this location. We can say that this is my x-axis, this is my y-axis. Obviously they don't have an actual position, but we can draw them at these particular positions. So we can say A equals AX, AY, and B equals BX, BY. Question is, can I somehow represent, because I'm starting to work with angles, and that means we kind of have to start thinking about trigonometry and stuff. Are there other ways I can represent these vectors? For instance, if I draw an image like this, and say I have a vector here, I'm going to call it V. Here's 1, here's my x-axis, here's my y-axis, here's 1. What can I say about Vx and Vy in this particular image?
Sine and cosine.
Okay, so this here is Vx, and it equals the cosine of this angle. So then we have to say, okay, if we in fact have an angle here that we'll call theta, if we have this particular angle between this vector and the x-axis, then the x-coordinates are certainly cosine of theta, and the y-axis, y is sine of theta. Then the question is, what if I draw it like this instead? This is the vector v, and here I have the angle. But I can't say x is the cosine and y is the sine, right? But almost. Like, what do I need to multiply the cosine with to get Vx? How can I scale both the sine and the cosine with the same number to get this? What is that number? length of the vector. So the length of v, that's one of the things I should then go back to the other side of the board and look at again. Okay, so we have dot product. One nice thing we'd like to do is say, what's the length of A? The length of A equals the square root of ax squared plus ay squared. If this is 2 dimensions, if this is 3 dimensions, I add az squared, and so on and so forth. So we've seen this before. I'd also like to say, because we use that sometimes in graphics to optimize our calculations, the length of A squared equals its x value squared plus its y value squared. And then we can add the z values and everything as well. But in some cases, we don't need to do this square root. We can actually work with it in the squared space, kind of. All right, so we have a way to calculate a length. And also we can say here, the cosine and sine of some theta, and this theta, in the case of every single vector that I can draw like this, and I can draw every vector like this, theta is the angle between the vector and the x-axis. So vector and x-axis, the angle between them I call here theta. Or I can say it's called theta v to differentiate it from other thetas. So if the vector isn't exactly 1 long, the original vector I drew that was here, that vector had exactly the length 1, and it's called a unit vector. This vector doesn't have the length 1, but I can say if I multiply it with its length, the cosine sine, then I get the coordinates of the vector. So I have a way here of switching between angles and coordinates of a vector, the angle and the coordinate. Fine. How can this help me here?
Subtract 90 degrees, the corner there, subtract the angle that B makes and the angle that A makes.
Okay, I can add at least and say this is going to be theta b here, and this here is going to be theta a. This has become tiny. I'm going to skip this a little bit and just have this big theta here. This is my main angle. Here I have theta a. Okay, so if I can figure these angles out, I'm not sure doing something like subtracting 90 degrees or something is gonna really work. These might be really close to each other, they might be far away. We have no kind of absolute values that we can use here. But we can at least represent them and say A equals the vector cosine, or let's say the length of A times the cosine of theta A, and the length of A times the sine theta A. Now I'm multiplying in here. Is there something there that we already wrote up that can make this a little bit simpler? B equals, do I need this length in here, like I have it here? Or can I simply say the length of B times the coordinate cos theta B sine theta B? So I'm going to do that for the upper line as well. So the length of A times this coordinate sine theta A. Okay, all I've done now though is represent the coordinates for A and B differently. We have to keep in mind what it is that we kind of know. What are the known variables here and what are the unknowns? So at this point, the known variables are AX, AY, BX, BY. The known variables here are, so we can calculate from that the length of A. Known variables are really not any of the angles yet. But still, we can say, okay, we know what cos theta A is, if we kind of divide it by the length of A, then we can figure that out. Now the question is with the angle between them.
Can you subtract the theta A, subtract theta B from theta A?
Okay. Another thing I know is that, yes, the theta that I'm looking for equals, doesn't really matter in which order we do it, it's going to be the same angle. But in this case, let's say theta A minus theta B, so it looks better on the image. Okay, so I can do this as well. So I have some kind of correlation here. Now, what I want to do at this point is I want to go ahead and say, I'm going to use a magic trick here, which is the dot product. And I'm just going to go in here and say, what happens if I simply take the dot product of A and B? What is the dot product of A and B? Just put it here. A dot B equals what? Can I use some of this? So it's going to be cos theta A multiplied by cos theta B, right? It's going to be the length of A times the length of B, because those are both here, and I can take that outside the scalar outside in the end. Times, and then I have cosine of one angle times the cosine of another angle plus the sine of one angle times the sine of another angle. Does this make sense? Am I doing my math correctly here? So either trying to remember your trigonometry or trying to Google it or something, is there a nice rule from trigonometry that tells us the multiplied cosines of two angles plus the multiplied sines of those same angles equals something? Do we have like a nice rule for that?
Like something like sine theta. We get to
The rule actually says the cosine of one angle minus another angle equals the cosines of each angle multiplied plus the sines of those angles multiplied. So it seems this kind of fits super nicely into exactly what we're trying to find here, right? Because right here we said, well, let's turn it around. A and B, but again, it's going to be the same angle. Because this is exactly how we defined our theta. So we can now say A dot B equals the length of A times the length of B times the cosine of theta. And we can just skip this parenthesis, which is the angle we were looking for. Which again tells us the cosine of the angle that we're looking for equals the dot product of these two vectors divided by the multiplied lengths of these two vectors. So what happens if again, not going to forget this. If I take a vector and divide it by its own length, A divided by A, or A divided by the length of A. You can say there's a certain thing we call a normalized vector, which equals that vector divided by its own length. And what that means is simply, if I have, it's hard to draw here, I'll just draw it. here. So this is the vector, let's call it R, and this here is the vector R normalized. It has the exact same direction, but it has unit length. So by dividing a vector with its own length, we end up with a unit length vector. We end up with a vector, whichever direction that it used to turn in, it is now length 1, but it has the same direction as the original vector. So we can rewrite this as well. Cosine of theta equals the dot product divided by the lengths, or we can say the dot products of the unit length versions of these vectors, or of the normalized vectors. This can be a better optimization for computers if we need to do this calculation. If they're not unit length already, it's best to do it afterwards, to just do it once, rather than take the length and multiply it into every single coordinate here, and then do the dot product. It's better to first finish the dot product, have only one number, and just have to divide with one number with this. So that's better optimization. The best optimization, however, is if you can somehow make sure that the vectors are already unit length before you start this. In that case, we like to view it like this. So if we have unit length vectors, then we're not going to do this whole thing. So if we can set up our program so that we're working with unit length vectors, even just one of them, this is something we're going to see a lot in lighting calculations. So when we start working with lights and lighting, we're going to do a lot of this. If we can work with unit length normals or some kind of unit length vectors, that's awesome. We can just multiply it like this. If we, however, end up not being able to work with unit length vectors, we'd like to save this multiplication until as late in the process as we possibly can. However, we now have a way to calculate the angle between two vectors. And before we're completely finished now, make sure I have a few minutes left. What can this tell us more quickly? What can a dot product now tell us more quickly than exactly the angle between the vectors? So, by doing the dot product, I can get, and dividing by the lengths, I can get the actual angle between two vectors. But in some cases, I don't really need all that. I just need some way, tell me something about the relationship between these two vectors. Like, what might I be interested in? Diagonal, perpendicular.
Yeah.
Yes, cool. So, if they're perpendicular, so if I have two vectors here, and they're exactly perpendicular to each other, that means I have a 90-degree angle. What is the cosine of a 90-degree angle?
0.
0, thank you. The cosine of a 90-degree angle, or the cosine of pi half, equals 0. Do the lengths matter? In this case, not really. If this is going to be 0, it doesn't matter what I divide this with or what I multiply this with, it's always going to be 0. So just by doing the dot product, and if we look at the dot product, it's a pretty cheap calculation. It's 2 multiplications and a sum. So just by doing that, just by saying here, let's go into the dot product again. If the dot product of A and B equals 0, that tells us that they are perpendicular to each other. That tells us that theta AB equals 90 degrees, exactly. All right, so that here we can get the exact angle just by doing the dot product. If we don't want to do the division, because it's not just the division that's costly, what's most costly is actually finding the length to begin with. Because finding the correct length will cost us a square root. And that's much more costly than most of the other mathematical operations that we do. Yes?
Yeah, I was just about to ask that tangent apparently is like more demanding operation. Like you could use reverse tangent to get it.
Yeah.
So,
But I imagine that it'd just be more costly in the end.
yeah.
So yeah, there are more ways to to get this, and we could use like arc cos, like the reverse cos or the inverse cosine operation, but that's a much more costly operation than what we have here. So either way, you can use that kind of to check your things when you're doing it on paper. Just use your calculator and use the inverse cosine function just to check that everything's correct. But in the end, we want to do this in computers, so we rather not have to do all of this exact stuff. So what, again, if it equals 0, it's perpendicular. What if we just check if it's bigger than 0? If the dot product is a positive number, what does that tell us about the cosine?
It's in the first column.
Yeah, let's just draw this again here. So is the cosine a positive number for this angle? Yes. Is the cosine a positive number for this angle? Yes. The cosine is always here, while the sine would become negative here. So the cosine is negative at this point, which tells us that if the, so it could be longer, it could be shorter, but we know that if the dot product is positive, we may not have the exact cosine, but we know the cosine is going to be positive as well, because the length is always a positive number, so we divide that by this, it's not going to change sign suddenly. But this tells us that if the dot product is bigger than 0, what does that tell us about the angle? Angle from A to B. Bigger than 90 degrees, smaller than 90 degrees. Okay, so smaller than 90 degrees. So if A dot B is bigger than 0, we have an acute angle. If A dot B is smaller than 0, that tells us it's bigger than 90 degrees, which means we have an obtuse angle. So acute angle, obtuse angle. This seems like something that could help us in, math and stuff, but it can actually help us in computer graphics as well, because this can help us optimize stuff in the Opengl pipeline. For instance, I have some kind of surface here, and this surface is facing somewhere, and there's a light that's facing it as well. And I can see that just by taking the, or let's not even use a light, let's say the camera, because that's even more important sometimes. Let's say this is part of an enclosed model. And so this normal kind of tells us that this is outside. You can tell just from taking the dot product of the vector to the camera and this normal, whether it's an obtuse angle or an acute angle. So we don't even need the lengths or anything, it's a very cheap operation. The fact that it's obtuse means that the camera can actually see it. No, sorry, the fact that it's acute. If, however, the camera were looking, or I'm checking for this angle here now, so I'm going to take a vector to the camera, I'm going to look at this normal here, which is the normal to this face here. Just by taking the dot product, I can see that the dot product will be smaller than 0, which means that this is bigger than 90 degrees, this angle here. And that simply tells me that if this is an enclosed space, there's no way the camera can see this. It's going to be behind the other ones. So if I know I'm drawing enclosed models, which is almost every single model in most regular computer games, if I know it's enclosed, then I can make this short check to simply cull all of the polygons that are turning away from the camera and only draw the ones that are at least somewhat facing the direction of the camera. And so I can take like more than half of my entire Opengl pipeline and you can just throw these things out and not do anything. And so I've optimized a lot without actually knowing that whether these will be seen or will not be seen. In some cases, we just do it when the lighting calculations happen. We just say, okay, I need to light this, but I can see already that it's not even facing the same direction, it's not even facing towards what I'm looking at, so I can just skip these things. I can just skip the lighting calculations, I can skip it all, because I know it won't be there in the final image. Other questions regarding this? So this is kind of just one of the ways we can use this simple calculation, just the dot product, without actually fully finding the correct angle, and just use what we know about the angle, whether it's acute or obtuse, to throw away, in many cases, half of everything that the OpenGL pipeline has to do, thus speed up the drawing of the entire frame and get a higher frame rate. If there are no questions, I think we're pretty much exactly done now. So, thanks for today. See you after the weekend.